Hi, and welcome to the 7th and last tutorial in our DIVA for Rhino tutorial series. In this tutorial, we will be running a thermal model, and we'll be linking that thermal model to the detailed lighting and shading schedules that we generated in our previous tutorials using DIVA and DASIM to have detailed dynamic shading control groups and detailed lighting control groups that will actually plug into the energy model as an input in order to test the relative effects of our different daylighting and control and shading control strategies on energy consumption for our office space. And as a reminder, we're using the reference office Rhino file, which you can download with this tutorial on the MIT Sustainable Design Lab website. And it's a south-facing side-lit office that's located in the Boston climate zone. And also as a reminder, just as it's important for all the tutorials, that this tutorial, it's critical that you run the previous tutorials before doing this final step of thermal modeling. That's because we are going to be utilizing the detailed lighting and shading control groups as schedules for our energy model, and you can only obtain those files by running the previous tutorials and having them stored in your local project directory. So the first step in running a thermal model is to set up the geometry for our energy model. And we'll be actually doing this with dedicated geometry that's independent of the surfaces that we're using for our daylight modeling. That means that we need to create geometry in the same place as our daylight geometry. That's all the surfaces are coincident, but that's simplified in a way that is appropriate for the energy modeling, because we don't need to have as many detailed surfaces for energy modeling. It's critical that the geometry is simplified and it's planar in order for the underlying energy simulation engine, which is Energy Plus, in order for it to process the geometry and provide us with an accurate kind of heat transfer model. So we'll begin by actually creating just a simple box for the geometry of our reference office. And I'll scroll down and you see that we have our DIVA thermal layer group that we haven't used yet, but it's in the model whenever we actually save our project and set up a location. That creates a layer structure that includes the DIVA analysis surfaces, but we also have these DIVA thermal layers. And so I'll go ahead and start with an adiabatic layer, which basically means that this is a layer that doesn't have any heat transfer. The surfaces that are on this layer won't experience any heat transfer. They will have thermal mass, but they won't have any actual transfer between them. And so the majority of my surfaces for the model will be on this layer because I'm assuming that this is an office that is within a larger building and it's sharing walls with other conditioned spaces. So I make that layer active and I go ahead and I'll click on the box tool to create a volume for our thermal model. We just want to have a simple set of surfaces, so the box tool is probably the easiest one to use. So I'll click on one corner and then click on the next, and I'll make the height the same as our daylight model height. And the next step is to then explode the volume that we created into individual surfaces so that it can be input correctly into the energy simulation engine. And so I'll go ahead and lock all of my daylight geometry on that layer so that I don't accidentally select any of those surfaces. And I'll select the volume that I created, and I'll just type in X for explode. And so I exploded that into 6 different surfaces. You'll see if I turn off the geometry layer, I have my 6 different surfaces for the 6-sided reference office. And I'm going to keep all of the outer floors, walls, and ceiling as adiabatic, but I'm going to change the outside wall as a wall in Energy Plus. And so I'll change its layer from adiabatic to EP wall. And I'll say, by right-clicking on it, I will say change object layer. So now I need to add a window. And to do that, I'll just actually scale the outer wall surface, the south-facing wall surface, according to the size of the window that I need. So I'll turn the daylight geometry, the lighting geometry back on, and I will use the scale 2D command to match my window to the window of my reference office. So I will select the wall and I'll type in scale 2D. This way it scales it within the plane of that south-facing wall. and I keep it in the right place. And I'll say my origin point is going to be the bottom of the surface, and I'll make sure that I type in C. Before selecting the base point, I'll type in C to make sure that I make a copy of that wall. And so I'll select my origin point here at the midpoint of the bottom edge of the surface, and I'll select the top, and I'll go ahead and drag it to the top of the window. And I'll scale it a couple times more horizontally and vertically to make it fit to my window using Scale 2D first. And I'll select that window, making sure that I didn't copy it this time, because now I just want to change its size. And I'll scale it once more, actually in one dimension, so I'll still type in Scale 1D, so that I can make that window a little bit shorter to match the geometry of the daylight model window. And once I've dragged that to the right position, you'll see that in perspective, it is coincident with the shape of the glazing. So if I go ahead and turn off the shading geometry, you'll see that it's about the same size. You'll see that this is on the wall layer. I select the window and it's on the DIVA thermal EP underscore wall layer. And so I'm gonna have to change that to the EP underscore window layer. And so I'll right click on window and I'll say change object layer. So what that does is if I turn off my daylight geometry here, you'll see that it's created a window surface that's coincident with the wall surface. And it's very important when creating geometry that the windows don't punch holes into the walls that host them. So this window isn't cut out of the wall, but rather it's in the same plane, it's kind of touching that wall and it's sort of overlapping with it. And that's critical for the way that we send geometry to Energy Plus in order to create an energy model. If I change the shaded, you'll see that this is not cutting a hole in that wall, it's actually coincident with that wall. And I go ahead and change it back to ghosted. I can change it to ghosted to see through and visualize it a little bit easier. It's also important that when creating a thermal model that those windows don't touch the edges of the walls that host them. Here we have a window that's offset a little bit, that's inset a little bit, that has some wall around it on all four sides, and that's critical in order to avoid any kind of complications in our energy model. And we also saw that if I turn my thermal geometry back on, you saw that the glazing for the daylight model is on the inside of the wall for my daylight model, and my geometry for my thermal model is actually matching the outside plane, the outside edges of my exterior wall. The thermal model is actually considering the heat transfer at the outside of the volume, at the outside of the exterior walls. And this minor discrepancy in distance for the placement of the window won't make a huge difference, but you can also set the geometry to the inside face of the daylight model and your results won't change that much. But for simplicity's sake, I'm actually just aligning all of my thermal geometry to the outside edges of my reference office. The daylighting geometry has a layer for shading, for dynamic shading, that is modeled explicitly in Rhino. For the thermal model, we don't actually have to model these blinds. The shading is going to actually be sent to Energy Plus as a dynamic shading device, and its presence in the thermal model will actually be as an exterior blind that is not explicitly modeled in Rhino, that will be scheduled according to the shading control groups that we ran in the previous tutorial. So if you remember, in that tutorial we used a DGP schedule, a daylight glare probability schedule, in order to influence the occupant control of shading, whether it's in the open position or the closed position. Well, the schedules that DIVA and DaySim generated in that exercise are actually stored in our local project directory. If I go to our local project directory, I have my project saved under the desktop, reference office T1, and I go to grid based. You'll see that there is a couple of CSV files in that directory. There's one with no shading that I ran earlier in one of my earlier tutorials, and then the later one is the reference office CSV file that has detailed dynamic shading. And so if I double click on that, you'll see that there are a series of columns and rows, and these are, you'll see that the first line is that it's called a DaySim schedule file to be used in combination with a thermal simulation program. The first three columns are month, day, and hour. And in this CSV file, we actually have a row for each hour, and we have 8,760 hours that are simulated. So we have, if we scroll all the way down, 8,760 rows, and each row has a different value for occupancy, for lighting for each control group. And so we have two lighting control groups, and so we have whether or not lighting is on for each control group, and there's a number if between 0 and 1 if it's off and full on. And we also have one for our lighting control group 2. So we have two groups, one with occupancy sensors, and then we have one with occupancy sensors and then photo sensor dimming. And then lastly, in our last column, we have our shading group. And so this shading, we have 0s or 1s for whether or not the blinds are up and down, and that's controlled by the daylight glare probability file that we also ran during our annual glare analysis. And so you remember we created an hourly map where we have the likelihood of whether or not occupants are going to be raising the blinds or lowering them, and so that schedule is reflected here in this column. So Energy Plus will actually be using these columns as schedules for lighting electricity consumption, so whether or not lighting is going to be turned on or off, as well as shading availability, whether or not the shade is going to be down or up in front of the window. And so this is where this file is located. So I'll go ahead and close that. So all that is to say that we actually don't need to have any kind of geometry modeled for our shading. So even though we have our detailed shading in our daylight geometry here, we don't need to have it for our thermal model geometry, which is a more simplified planar model. So I'll go ahead and turn the geometry off again for the daylighting. And one last thing to check for our model is to check the surface normals, which is basically the direction that each surface is facing. Whenever you model a surface in any kind of 3D geometry, it always has a directional normal, and that's perpendicular to the surface, and it's either pointing up or down, or away from the geometry or into the space. And to check that, we type in dir in Rhino, and if I'd selected one surface and I hit enter, you'll see that the surface normals are pointing outward. They're not pointing into the space. And that's because I modeled this initially as a box. And so whenever you begin creating a geometry as a closed volume like a box, the surface normals are always pointing out. And since I exploded that box into individual surfaces, I can expect that all of these surface normals, so if I go ahead and select all of them in one fell swoop and I hit enter, you'll see that they all actually point outward. All of those white normals are pointing outwards. So these are the normals pointing outward for the ceiling and the floor and the walls, and you see even the window. If I type in dir again, and I'll go ahead and check that window, you'll see it's pointing out. And for some reason, if it was pointing inward and we needed to flip it as a correction, we can go ahead and just type in flip, and that will flip the geometry. But we don't need to do that for any of our surfaces because they are all actually pointing outward correctly. Okay, so our next task is then to assign materials to these surfaces that we created for our thermal model. So I'll go ahead and I will click on the materials button, and there's a sub menu, a list of other options for materials, and I'll click on assign materials. Now you'll remember from when we were doing a daylight model that we have our set of daylight materials, and for each layer in our geometry layer group, we can assign a material that's linked to our radiance database. But we're actually using a thermal model, so we have to click on the thermal materials tab. So click on that and you'll see that the only layers that are available to assign materials to are the sublayers within the DIVA thermal layer group. So I have adiabatic, ceiling, floor, wall, window, and shading. And I don't need to use all of these layers because I put most of my surfaces on the adiabatic layer. And so for adiabatic, I do need to give it a material, even though there's no heat transfer. There's some properties associated with thermal mass that are associated with the material that we choose, so we do have to select something. So for adiabatic, I'll go ahead and just pick a wall for climate zone 4 through 8. pick this one. And everything is on adiabatic except for the outside wall. We don't have any ceilings or floors. It's all on this layer. But we do have a south-facing exterior wall that's going to be on this layer. And I'll go ahead and select that same layer for the wall, the climate zone 4 to 8 exterior wall, steel framed. That's associated with the ASHRAE standard 90.1 2010. And we also have a window in our model, so I'll go ahead and select glazing double pane low E argon filled. You can pick any of the glazing layers. And shading, again, we don't actually have any shading that needs to be assigned for this experiment. If we had external shading like overhangs or fins or even adjacent buildings, we would assign that material to that. But we are using the schedules for dynamic shading, and that's associated with an external shade that Energy Plus assumes is going to be either fully open or closed according to the schedule, and it doesn't need to have an assigned material associated with it on our end in this model. So I don't need to assign anything to that. And so I'll go ahead and say submit material information. And the last step is then I'll just go ahead and change this back to wireframe, and I'll turn this geometry off so we can just see our thermal model. The next step is to then click on metrics. You'll see that we have our daylight images, our daylight grid-based tabs for the different types of simulations that we ran previously in the previous tutorials, but now we'll actually be using this last tab, the thermal single zone energy model. It's a single zone because there's only one thermal zone in our model. This tool is really only capable of doing one zone, and so that's why it's called single zone. We're just looking at this one space of our reference office. And you'll see that we have a series of parameters that we need to specify in order to run a thermal model. And that begins with occupant density. And so this is basically saying how many meters squared are there per occupant. And the default is 10. And then we can change that depending on the specifics of our space. In our model, we have, if you remember, we have 6 desks, and our surface area is about 30 square meters. And so our occupant density then, if we have meters squared per occupant, if we have 5 occupants and about 30 square meters, so our occupant density is about 5. But if we're expecting 2 people to sit at each desk, we can, always increase that back to 10. But I'll go ahead and make it 5. Next is equipment power density. This is also known as plug loads. And so this is the watts for your equipment per meter squared of floor area. Now 4 is like a kind of a lower on the lower end of the spectrum. For an office, you might expect to have something closer to, let's say, 11 watts per square meter as a kind of conservative number. That's the same as about 1 watt per square foot. So I'll go ahead and just increase that to 11. And the next is air changes per hour. So this is basically the frequency with which fresh air from the outside will enter our space through leaks and cracks in the construction. And so it can be thought of as associated with air tightness. And this is happening kind of at a natural rate. And this is a function of the volume of the space. So let's say we had 100 cubic meters. And if our air changes per hour is 0.5, that means 50 cubic meters of fresh air is coming into the space every hour. And 0.5 is like an average kind of air tightness for new construction. It's not that well sealed. If we're talking about newer standards for air tightness, I could change this to 0.3. And so this would represent a well-sealed building that is has a relatively high level of air tightness, and it's not very leaky. And maybe that's what you can expect for a newer office construction. And then moving down to conditioning systems, you'll see that we have heating efficiency and cooling efficiency. And so this is basically the efficiency of the performance of our heating and cooling systems. So when we run an energy model, we typically get a thermal load for heating and cooling, how much heating energy is required to reach our comfort level temperature inside in the winter, and then in the summer, how much cooling energy is required to lower the temperature inside to a comfortable level. And then that load divided by this efficiency is basically your energy use. And the default heating efficiency is 0.8. And this is kind of like the minimum requirement for ASHRAE for, let's just say, like a gas-fired boiler. But I'll make that a 0.9 because typically you find more energy efficient boilers out there that are a lot higher efficiency than 0.8. And then cooling efficiency will be the same thing. This is basically the coefficient of performance for an air conditioner. 3 is like an average value. You can get much much higher, more efficient cooling systems by looking up different types of cooling equipment. The efficiency can be much higher than that, but I'll go ahead and leave it as 3. Then our next values are for cooling set points and setbacks. And so basically the cooling set point is at what temperature in degrees Celsius do we want to maintain when the building is in cooling mode, like in the summer. And so we can leave that as the default at 26. And then a setback is that when we are beyond our occupancy schedule, so beyond the occupancy of 8 to 6, whenever the building is not occupied, the temperature will be set back, the thermostat will be set back to a higher temperature so that we preserve cooling energy. And so that by default is at 32, and we'll leave that. And then the same is true for heating set point and setback. Basically, we want to say at what degrees Celsius are we okay with as comfortable for our heating season, and we can leave that at 22. And then when the building is not occupied, how far down do we want to set that back so that we're not overexerting our heating system when the building isn't occupied. And so I'll leave those as the defaults. And so even though I changed some of these values, you can, it's okay to leave these as the defaults, but just know that some of by changing these values will have a significant impact on the energy performance of whatever you're testing, and that you'll probably want to keep these consistent when you're experimenting with different daylight or control strategies. So these should just really remain as a constant. And we'll leave natural ventilation checked off for this tutorial. Okay, so then next we hit Run Simulation. And another dialog box pops up. And this dialog box has to do with thermal shading and electric lighting schedules. And so if you're doing this tutorial in sequence, and so if you've already done your electric lighting control groups and you've already set up your shading control groups and run a climate-based simulation to create the right schedules in your local project directory, this dialog box should show up. Otherwise, you'll get an error saying that DIVA could not find any kind of dynamic shading or lighting schedules associated with your file. So the fact that you get one of these dialog boxes after you've run the previous tutorials is a good sign. And so here it's actually asking you to assign information for shading and lighting. And so since we only have one shading control group for those blinds that are in front of our window, it's only going to give us one group and one option to input the shading into Energy Plus. So it asks for the shaded geometry layer. So not actually the shading, it's not actually the shading geometry, but it's actually the geometry of what's being shaded in your energy model. And so it's going to be typically your window layer. And so it knows that the window layer is actually associated with a window surface, and that's the only type of surface that can be shaded in your energy model for this type of dynamic shading. And so I'll go ahead and leave that as the default and keep that selected as EP_window. That's the geometry that's going to be shaded. And then we have to assign what type of shading material. It's asking us to select which of the Energy Plus categories do we want this shading to be associated with. So we have the choices of either having it an exterior or interior blind or an exterior and interior shade. So I'll go ahead and just say exterior shade since we have it modeled as fins on the exterior of the building. And so as I mentioned before, Energy Plus will be using the shading schedules that we created when we ran our shading control group experiment, and it's going to be using that to determine whether or not this exterior shade is going to be lowered or raised. And then the next option for our shading and electric lighting schedules dialog box has to do with the lighting information. And so you'll see that there's a schedule availability prompt for each lighting group in our model, and then this is associated with the lighting control groups that we ran in our previous tutorial. So there's the first lighting control group that is only controlled by occupancy sensors, and so whenever there's occupancy, it's always on. And the schedule availability we'll just say that this schedule is available, and we're going to have Energy Plus use that schedule to determine the lighting energy consumption. And then the next group is the second control group, which has also occupancy sensors, but it is controlled by photosensor dimming, and we'll also make sure that is on. So after we've assigned the shading and lighting information, we can go ahead and say submit schedule information, and this will actually run the energy simulation, and we'll put the Energy Plus command line in motion. So you'll see that the command line comes up. So after our thermal simulation is complete, we get a simulation report that automatically pops up. And the report begins with monthly and hourly energy use graphs. And so I'll scroll down a little bit to make that more clear. So you see that for the monthly energy use, we have a graph that shows us the energy consumption in kilowatt hours in the y-axis and monthly end use results in the x-axis. And each end use is divided up by lighting energy, cooling energy, heating, and equipment. And so you see that we have an expected pattern for more heating in the winter and then cooling energy consumed in the summer. And then we have a kind of consistent band of equipment energy that is always at the bottom of our graph. That doesn't really change because the equipment energy doesn't change much as a result of anything. It's really just based on occupancy. And the lighting energy is relatively low because we're using our photosensor dimming for one of the groups, which is really going to reduce the lighting energy consumption. So if we scroll down, we see that we have the heating and cooling energy consumption hourly map. And so this is a kind of an annual hourly map for heating and cooling throughout the year. And so we have, again, the months in the x-axis. And then in the y-axis, we have every hour of the day, so from 0 to 24. And then the blue and red is a kind of intensity map of heating energy and then cooling energy in blue. And so you'll see that in the winter, we typically have an increase in heating energy consumption at the start of the day because this is when our setback turns off and then we have our set point turning on. And so our temperature for our energy balance increases, and so the energy needed to heat that space has to actually jump and exert itself even more in order to maintain comfort levels inside the space. And so that's why we have a more intense energy consumption for heating in the morning hours in the winter. And then the rest of this report is more of a detailed kind of summary that's automatically generated by Energy Plus of our zone. And so it has input verification and results summary, and it has some climate data, and there is a cooling summary that's monthly, and as well as a heating summary, and then also it's followed by space gains and then a window report. And so if you scroll down, you'll see that there's climate data, there's some information on window to wall ratio, as well as skylights if we have them, and then there is a zone summary for all of the different components of our model. It's automatically generated by Energy Plus. And I won't go into these details for this tutorial, but you can scroll down to look at some more fine-grained information about the performance of your model. So I'll minimize that. And okay, so let's find out where these results are actually located so that we can analyze those results and understand them a little bit better. So if we go back to our desktop, which is where I save my file, if we go to the local project directory, I have my file saved on the desktop, and so it's called Reference Office T1. And if I go to thermal, the thermal subfolder, this is where all of the results are stored. And you'll see that for one simulation, it's generated a number of files. There are some behind the scenes Energy Plus files like the IDF file as well as DXF files and so forth that are used by Energy Plus and generated and saved here as a record for our model. But then there's also some output results files that are both CSVs and PNGs. So the PNG files are basically those two monthly and hourly image graphs that we saw in our report. And then the CSV files are basically spreadsheets that communicate the energy results for different time periods. And those time periods run from hourly to daily to weekly to monthly and then annual. So for an example, I'll double click on the annual results. So you see here it starts with the name of the file and then the number of the iteration. I ran one iteration, so it has a suffix of 1, and then annually SI means the type of units that it's in, Standard International. I'll double click on this and it opens up in Excel, and you'll see that for the annual results there are 5 rows, and each one represents an annual sum for all of the inputs. We can ignore the first one because it's really just the air temperature, which is more important. The air temperature, this zone air temperature becomes more important for the hourly results, but it doesn't really make sense to add up these temperatures. It's only significant for the hourly, so I'll go ahead and ignore that one row. And then the next 4 are our end use variables. So we have, again, as you remember, electricity for interior lights, equipment, and then heating energy and cooling energy. And here are the annual results. These are added up. they're added up where we saw them previously both in monthly results and hourly results, and here are the annual totals. So if I want to know how much energy my reference office is consuming for the whole year, I'll go ahead and just do a sum of those 4 end uses: electricity for lights, electricity for equipment, and then heating and cooling energy. And I'll sum those up, and you'll see here I have an annual number in kilowatt hours for my reference office for the whole year. It's almost 3,000, consuming almost 3,000 kilowatt hours for the year. And this might not mean very much because the number of total kilowatt hours always depends on the size of your building. And so to have a sense of the intensity of energy use for our space, I can divide this or normalize it by the floor area of our building so that we have a number that we can use to compare to other types of buildings. And if you remember, the floor area of our reference office is 29.5 meters squared. So if I just take an area, if I go to my geometry here and I type in the area and I select the floor area for my reference office, it's 29.52 square meters. So I'll go back to Excel. I want to know what the energy use intensity is. So I'll say this cell is equal to the total energy use, which is the value here, divided by the area of the floor area of my reference office, 29.52. And so you'll see that here is the kilowatt hours total. And then here is the kilowatt hours per meter squared, or EUI. And so that comes out to about 100.5. Now we can use this number as a basis of comparison for different lighting control strategies. We already have a lighting control group and a shading control group set. And so why don't I just do a quick test to see what would happen to the energy use intensity for our reference office if I were to make a change to the lighting control groups, for example. So if I go back to my model and I will temporarily turn off the thermal zones, and let's just say I go in here and I go back to lighting controls, and let's look at what would happen if I actually did not have photosensor dimming for my second lighting control group. So let's just say it's back to a manual on-off switch. So I'll go ahead and make that change, and I'll say submit. I'll have to run another climate-based metric, so I need to go back to daylight grid base, and I'll go to climate-based. And I will say run simulation in order to regenerate my lighting schedule according to this changed lighting control group. And it's going to ask if I want to reuse the daylight coefficients in the model. And so this is important to note. If we didn't have any lighting control groups set and we hadn't initially run a climate-based metric, we would not want to reuse these coefficient files. We want to rerun the climate-based metric from scratch, especially if geometry or materials have changed. But since we've already run our lighting control groups and our detailed dynamic shading, we can reuse the daylight coefficient that's already in the file. And so I'll go ahead and click yes, and this will dramatically speed up the simulation time, as you remember from the previous tutorial. So just like before, we get our load DIVA metrics dialog box, and I'll go ahead and say load simulation data, and our report will be generated. And so in the previous tutorial, in lighting control group 1, we had occupancy sensors, and so we maintained that lighting control group. But in our initial tutorial for lighting control group 2, we had both occupancy sensors as well as photo sensor dimming. And here I turned off both, and so we really have just manual controls, which, as you can see, it causes the light to be turned on much more frequently than we previously had with photo sensor dimming and occupancy sensors. And so this we would expect to have some impact on the lighting energy in our model. So I'll go ahead and minimize that, and I'll turn the DIVA thermal back on. And I'll go ahead and run another thermal analysis. Now the fact that I ran a climate-based metric with a new lighting control strategy, so basically I decreased the performance of our lighting control. Instead of using photosensor dimming that I had carried over from a previous tutorial, I kind of made that second lighting control group worse by making it just manually controlled. And so that control group is going to be updating the lighting control schedule that's sent to Energy Plus. And so that should influence the energy performance of my reference office. So if I keep the same settings that I had before and say run simulation, and now it's asking if I want to use those schedules, you'll see that the lighting information has been updated. I didn't really do anything to lighting control group 1, but I changed lighting control group 2 from occupancy sensor with photo sensor dimming to just manual controlled, and I'll keep that as on. And so this should reflect a change in our energy performance. And a new simulation report pops up, and you'll see that the lighting energy has increased a little bit from our previous thermal simulation. If I go back to the previous simulation and comparing that to our energy use from before, you'll see that the lighting energy has increased. So you'll see that because of the additional lighting energy that's being consumed, there's actually heat given off by those electric lights. And that extra heat that we're going to have because of this increased lighting energy use is actually going to reduce our heating load a bit, which is why our total, let's say if we look at the month of January, our total energy use stays the same, but the balance between lighting and heating is going to be a little bit different. So if I do another comparison, if I just go quickly back to my initial energy analysis and we'll just look at January, the total energy stays the same for that month, but in the initial iteration there's more heating and less lighting, and now in my current iteration, I clicked on this current one, we have more lighting because of our lighting controls have decreased in performance, and our heating energy is a little bit lower because our load is lower because we're using a little bit of that the additional electric lighting energy for sort of borrowed heating. But the difference in terms of total energy use becomes apparent in the summer. Because we have more electric lighting and more heat given off by those lights, the amount of cooling has to increase. And so if I again compare it to the previous graph, if I click on my first iteration, and we'll just focus, let's say looking at the months of June, July, and August. If I go back to iteration 1, that cooling energy was much better before. It was a lot lower, and our lighting energy was lower. But if I click on my second iteration where I have a worse lighting control group, you'll see that the lighting energy increases, and so does the cooling energy, in order to compensate for the increased amount of heat generated by those lights. And now to just get a sense of what the bottom line is, if I go back to my CSV file that I had manipulated for the first iteration, I basically just created a total number for that initial iteration for the annual sum of lighting, equipment, energy, and cooling. And I gave it a normalized value. I calculated a normalized value for the energy use intensity. So now if I go back to my local project directory under thermal, that same folder where I opened up an annual analysis for the first iteration, and if I scroll down, let's just say I organize these by type. Here's my annual result for that first iteration, and then let's go and open up the annual result for the second iteration. That's located right here. It has a tag of 2, showing that it's the second iteration. So if I open that up, I have the same end use values, I have the same end use variables, and if I go ahead and copy all those values into my initial scheme, I can go ahead and paste them right here, and I copy these functions over to this new column, you'll see that the total kilowatt hours has increased, and then our energy use intensity has also increased by about 5 points, from about 100 to about 105. And you'll see that that's because of the increased lighting load or lighting energy consumption, as well as the increased cooling associated with that increased lighting energy in the summer. And so I encourage users to experiment with different lighting control groups by looking at the different lighting control groups and thinking about the steps that we did in the previous tutorials for lighting controls, as well as dynamic shading. If I go back to the shading controls, so our different shading. So thinking about the trade-offs between the glare performance, and daylight autonomy performance, as well as lighting energy, and then running those different schedules in a thermal analysis by experimenting with different combinations of lighting control groups and shading controls to see how these different strategies can improve the overall energy use, and finding the right trade-off between daylight performance and energy performance. So that about sums up the integrated energy and daylighting analysis for this tutorial, and that also wraps up the DIVA for Rhino tutorials for this specific tutorial series. Thanks a lot for taking the time to follow through all of these tutorials. It's been a pleasure, and I hope that you've learned a few things about DIVA and that you feel more confident running daylight analysis with detailed lighting and shading controls, as well as running an integrated energy analysis to inform the way that you design and to empower you to evaluate the relative performance of different daylighting and shading control strategies. Thank you.